Hi Math 30s. This video is going to be on lesson 5 in your workbook on page 317 under the unit polynomial functions. What we're going to do is we're going to do a quick review of a concept in 20-1 and then I will do 2 class examples in this video. So your review from 20-1, it says consider the polynomial function. So it gives you this function here. And what it says is this function can be expressed in factored form. So you would have done this in 20-1, right? If you're given a quadratic, factor this quadratic. So what two numbers multiply or give you a product of -6 and sum to -1. And the two factors would be x plus 2 and x minus 3. The reason why we factor in 20-1 is because once we have it in factored form, we could get the zeros or the x-intercepts of our graph. So based on these factors, if I want to find what the zeros are, I set each factor equal to 0, and then I solve for each factor. So x plus 2, if that was set equal to 0, this x would be x is equal to -2. If you set this guy equal to 0 and solve, that x would be 3. What the zeros give you is x-intercepts on your graph. So this is the quadratic here, and we've got an x-intercept of 3, and we have an x-intercept of -2. Remember that this is your constant term. The constant term is always going to be the y-intercept of your polynomial function. So this y-intercept is down here at -6. So the reason why we factor again is because we want to know what the x-intercepts of the graphs are. So just to fill this in, it says the graph of this function here has the x-intercepts of -2 and 3. These can also be called zeros. They're the zeros of the function. And the reason why these are zeros is because when x is 3, what's the y-coordinate is 0, right? So the reason why they're zeros is because the corresponding y-coordinates are 0. So it says the function has the zeros, -2 and 3. If I set this equation equal to 0, then the roots of the equation are the same numbers, -2 and 3. So what it's just sort of saying is that whether I use the term x-intercepts, I'm going to be talking about the graph. If I talk about the function itself, I'm going to say the zeros of the function and then the roots. Those three can be used interchangeably. So when it says fill in the blanks, again, if we're talking about the function, I'm just going to use the term zeros. So the zeros of the function. Now it wants to talk about the graph. On a graph, they would be x-intercepts of the function. And then if we're talking about an equation, they're going to just use the term roots. So whether it's zeros, x-intercepts, or roots, they're all the same numbers. Okay. Let's get into this lesson now, which is called the integral zero theorem. So if you want to highlight the integral zero theorem, we will get into that. It gives you a polynomial here, and it's a quadratic. So the reason why they're starting with quadratics is because you could factor quadratics from 20-1. So it says the factors of this polynomial function are these two factors here. What are the zeros of the function? So remember, zeros are the same thing as x-intercepts. If this was set equal to 0, one of my zeros would be -8, and that 0 would be 3. What it says is, what do you notice about the constant term? So this is my constant term, and the zeros of the polynomial function. So how are -8 and 3 related to this constant term? What you'll see once we do a couple of these examples is -8 and 3, they are actually factors of the number -24. These are factors of the constant term. So let's just write that down and then I'll explain it. So let's write the zeros. And remember the zeros were -8 and 3. Those zeros are factors of the constant term. So from 10C, if you were given a number and I said to you, what are all the factors of this number? You're looking for all the numbers that divide evenly into this number. So for example, 1 is always a factor, and the number itself. 24 is divisible by 2. It goes in 12 times. 24 is divisible by 3. It goes in 8 times. 24 is divisible by 4. It goes in 6 times. These are all of the factors of the number 24. Because what you also need to do, though, and we didn't talk about this in 10C, is for all of these numbers, I could write the positive or negative for each of these. So what I'm sort of saying is, if I give you the number 24, it's divisible by 3 and by negative 3, right? 24 is divisible by 12 and negative 12. So this was the constant term, and there's 8, which was a 0, and 3, which was a 0. Okay. So again, just to see this in one more scenario, they give you a third degree polynomial function. It has 3 factors. That means if these are factors, they're x-intercepts or zeros of the graph. So I've got a 0 at 2, an x-intercept at 2. I've got an x-intercept at 1 from that factor, and this factor would give me an x-intercept or a 0 at -1. These are the zeros or the x-intercepts of my graph. How are these numbers related to the constant? These numbers are all factors of the number 2. Because if I said, well, what are the factors of 2? Plus or minus 1, plus or minus 2. Those are the factors. So again, the zeros, these 3 numbers here are factors of the constant term. What this leads into is something called potential zeros. So I'm going to show you what potential zeros are. It's on the next page. Okay, so there's a new theorem. It's called the integral zero theorem. So just highlight that. Doesn't need to go on a study guide or study sheet, anything like that. I'm just going to explain how this works and then how you would use it. What the integral theorem states is that the zeros of a polynomial function, they're always going to be factors of the constant term, which is what we just did in those 2 previous examples. So zeros will always be factors of the constant term. So what's going to happen is they're going to give you a polynomial function such as this. And one of the things they could ask are, what are the potential zeros? So we know, according to the integral zero theorem, that zeros are always factors of the constant term. So here's my constant term, -6. What are the factors of -6? You list them all, and they would be what's called the potential zeros. So the factors of -6 are plus or minus 1. 2 is a factor of -6. 3 and 6. These are all of the factors of the constant term. These are all potential zeros. Okay, now which one of these are true zeros of this polynomial function? Like, what are the true x-intercepts? Remember that a degree 3 tells you that your polynomial function could have a maximum of 3 x-intercepts. So what I want you to do is I want you to take out your calculator and I want you to enter this polynomial function in y1. And I'm going to show you how we could see which of these numbers are going to be zeros. So if I take out my calculator and go to y1, here I have it inputted. And I'm going to look at the graph first of all. So this graph does have 3 zeros. These are 3 x-intercepts, these are 3 zeros. I'm not going to count 1, 2, 3. Where I want you to see what the zeros are is I always want you to look at your table. If you go to your table, what you are looking for is when y is equal to 0. That means that this is an x-intercept. There's an x-intercept at -2, at -1, and at 3. Those are my 3 x-intercepts of the graph. So the zeros of this polynomial function are -2, -1, and 3. So let's write that down. So the zeros of the polynomial function are -2, -1, and 3. Now, once I know what my zeros are, I could actually give you the factors of the polynomial function, because in order to get a 0 of -2, one of my factors has to be x plus 2. In order to get a 0 of -1, x plus 1 must be a factor. And in order to get a 0 of 3, x minus 3 is a factor. I've actually completely factored this polynomial function just by looking at the table. Now, what I just showed you, like this thing about looking at your table, it's a little bit of a cheat that you would do. I know the answer without really doing any of the work. And I'm going to show you now, well, how would you do the work? So what a question would say is it would say factor the polynomial function, completely factor this, and this is the answer completely factored. But it will always say how they want you to factor it. So they might say using the factor theorem, or they might say using synthetic division. And then if you just give the answer with no supporting work, your answer would not get any marks, even if it's correct. So I'm going to show you using the factor theorem to start with. And then once we use the factor theorem, we always go into synthetic division. So how I'm going to show you how we would get this is I know on my calculator that these are the zeros. Pick one of these to start with. It doesn't matter which one. I'm going to just pick -1. And what I'm going to do is I'm going to input into my polynomial function -1. So wherever I see an x, I'm going to take that out and I'm going to put it in -1. So -1 cubed minus 7 times -1 minus 6. P of -1 is equal to -1 plus 7 minus 6. P of -1 is equal to -6 and -1 is -7. -7 plus 7 is 0. If I said I want you to completely factor this using the factor theorem, this is the work that you would need to show. Because according to the factor theorem, remember, as soon as you get a remainder of 0, then according to the factor theorem, x plus 1 is a factor. So you'd say since P of -1 is equal to 0, whenever we get a remainder of 0, x plus 1 is a factor. So this is how I would show the work to get that answer, to get that factor, okay? Now, I could continue using the factor theorem, and I could input P of -2, and I would get 0, and that's proving that x plus 2 is a factor, and I could input P of 3, it would give me 0, and it would prove that that's a factor. But what most students do, and what I find the most efficient, is show me using the factor theorem one of your zeros. So I just took care of that guy. Once you've proved that that's a factor, we're now going to go from the factor theorem into synthetic division. Okay, so how would we do that? So I'm just going to go down here. It says completely factor the polynomial. So remember that we need to be in descending order of x, and we need zeros as placeholders. So the polynomial is x to the 3 plus 0x squared minus 7x, and the constant is -6. So set up using synthetic division, your upside down division bar, and you're going to put a 1, a 0, a -7, and a -6. I just showed using the remainder theorem, or sorry, the factor theorem, that this is x plus 1 is going to be a factor. So I'm going to take that -1, and that's the one I'm going to, because I've just proved that, I'm going to use that here. So let's carry out our synthetic division, and that would give me, bring down the 1, carry out your multiplication, and then you're going to add. Multiply, and then you're going to add. -7 plus 1 is -6. Multiply, you'll get 6, and then you'll add 0. So there it's showing you through synthetic division that -1 is a 0. But what this has just done, this gives me my quotient. Is, remember, if this was a third degree polynomial, my quotient will be a second degree. So that would be 1x squared minus 1x minus 6. Now I could write my polynomial function as follows. P of x is equal to, it's always dq plus r. So your divisor times the quotient plus the remainder. So the divisor, in order to get a -1, would be x plus 1. The quotient would be this guy. From here, as soon as you get to a quadratic, you're able to factor this how you would have factored in 20-1. So what gives you a product of -6 and a sum of -1? So what two numbers multiply to -6 and add to -1? So that would be -3 and +2. This, I'm just going to bring down that factor, and then I'm going to put P of x is equal to. This is my completely factored answer, which I'd actually seen, I already knew that before I even started this question, right? So that is my completely factored answer, but here I've done all the work to support it, okay? If they said completely factor, this is what you would get. This would be completely factored. If it said solve, it wants what are the x-intercepts. So when we solve, what we're going to do is we're going to let our factors equal to 0. So you're going to write x plus 1, x minus 3, x plus 2. When you're solving, you must write equal to 0. From here, you can look at each factor and say what the root of each factor would be. So this factor would be -1. This factor, the root would be 3, and this factor would be -2. These are the zeros or the roots or the x-intercepts of my graph. So just make sure you're paying attention to how they're asking, what they're asking for in the question, whether they want it written in completely factored form or whether they want you to solve it or both. So let's do one more class example, and then I will give you homework to practice. Okay, consider this polynomial function. List the potential zeros of the polynomial. So again, potential zeros, they come from the constant term, which is 12. You need to look at the constant term and you need to list what are all of the factors of that constant term. So the factors of 12, the numbers that divide into 12 are 1 and 12. 2 is a factor of 12 and it goes in 6 times. 3 is a factor of 12 and it goes in 4 times. These are all of the factors of 12. Now to make them potential zeros, they're the potential zeros, but I need to put a plus or minus in front of each one. Okay, those are the potential zeros. Express the polynomial in factored form. They want this guy completely factored. We're going to start by using that sheet on our calculator, and then we are going to, from there, we're just going to actually show the work. This, remember, is a 4th degree polynomial. That tells you that there could be up to 4 x-intercepts on the graph. So let's actually enter this into our y1. Let's look at the graph, see how many x-intercepts there are, and then let's factor this guy. So go to y1 and type in x to the power of 4 plus 2x cubed minus 7x squared minus 8x plus 12. I'm just going to look at the graph really quickly and look at, there are actually 4 x-intercepts. I'm going to look at the table, so that means that there's 4 zeros here. I'm going to look at the table, and I'm going to look for the zeros. Here they are. -3 is one of my x-intercepts. -2 is an x-intercept, 1 and 2. So the zeros of this polynomial function are -3, -2, 1, and 2. So I'm just going to jot that down. Zeros. I know that they are, I keep forgetting, let me go back. Okay, -3, -2, 1 and 2. based on these zeros, I can find what the factors are. In order to get a 0 of -3, x plus 3 is going to be a factor. In order to get a 0 of -2, x plus 2 is a factor. In order to get a 0 of 1, x minus 1 is a factor. And the last factor, x minus 2. Because they wrote this polynomial function using p of x, I'm going to write p of x here. This is my answer, okay? This answer, though, without supporting work, would not be worth anything. So what you have to do is because it will almost always say like prove using the factor theorem or something like that, pick one of these zeros to plug into this polynomial to show that the remainder is 0. And then we'll start doing synthetic division. So for example, out of these numbers here, I'm going to put in a 1, because the reason why I often always choose 1 is because it's going to make the math really easy to do in your head. So let's choose the 0 of 1, and let's write p of 1 is equal to, every time you see an x, input a 1. Plus 12. P of 1 is equal to 1 plus 2 minus 7 minus 8 plus 12. This is -15, 12, and this would be positive 15. P of 1 is equal to 0. According to the factor theorem, since P of 1 is equal to 0, if you get a 0 as your remainder, what that tells you is x minus 1 is a factor. If you showed all of this, you would then get a mark for that at least. Okay, you could continue on. You wouldn't want to continue on with the factor theorem, because we need to give it in completely factored form, and you would need to show me now using synthetic division. So this is in descending order of x. I don't need any 0 placeholders, so let's put our coefficients of the coefficient of each term, and let's carry out the synthetic division. So 1 to -7, -8, and 12. Use the one you just used for your theorem, right? So I'm going to put my root of 1 here, the root of my divisor. Drop your 1, and from here, carry out your multiplication. Carry out your addition, multiply, add, multiply, add, multiply, and when you add those two, you get 0. This, remember, is your quotient. If this was a 4th degree polynomial, and it was, right? This is a 4th degree polynomial. This quotient is going to be a 3rd degree polynomial. So this would be x to the 3 plus 3x squared minus 4x minus 12. Where I'm at now with factoring is the following. P of x is equal to, I get to list the factor that gives you a root of 1, so that would be x minus 1. Then I now write my quotient. Okay, from here, what I now need to do is I need to continue on with this guy. I need to factor this. This is what I'm going to now be putting under my upside down division bar, because I need to factor this. So I'm going to put a 1, a 3, a -4, and a -12. Now, what number am I going to put for my divisor? I'm not going to put the 1 again because I've already used up the 1, right? I've already showed that 1 is a factor. So I'm going to go to a different 0, and I'm going to just say, I'm going to go to this one. I'm going to say 2. So I'm going to put the 2 here. Watch what will happen when I put the 2 there. If I carry out my synthetic division, I drop the 1. 2 times 1 is 2. Add, and you get 5. 5 times 2 is 10. Add, and you get 6. 6 times 2 is 12. Add, and you get 0. What is happening now? This is now my quotient. This was a 3rd degree factor, so my quotient is going to be a 2nd degree. So that would be 1x squared plus 5x plus 6. Okay, remember, once you get down to a quadratic, you could then factor by your PSA method. But I'm going to rewrite the polynomial function where I'm at. P of x is equal to, I already have this factor. Now I could write this factor. So the factor that gives me a root of 2 would be x minus 2. Then I write my quotient. And then from here, I could factor this. So what are the two numbers that multiply to 6 and add to 5? A 2 and a 3. Bring down this one, which you've already solved, and bring down that guy. And that is your completely factored polynomial. So A said, what is a completely factored polynomial? Or express the polynomial in factored form. This would be the polynomial in factored form. Sorry, A was a potential zeros we did. B was the polynomial in factored form. C is the zeros. I could now look at my polynomial and I could get my zeros. So the zeros are 1, 2, -2, and -3. State the roots of this equation. Remember that x-intercepts, zeros, and roots will all give you the same number. So the roots of this equation will be a 1, a 2, a -2, and a -3. I'm going to give you your homework. Because there was only one question where they fully factored a 4th degree polynomial, I want to do one more with you. But those of you that don't think you need it, you could go right to this homework if you wanted to. There's 2 podcast lessons that correspond to this, so podcasts 7 and 9. Those of you that want to see sort of one more comprehensive example, I will quickly do 10b. So if you want to flip to 10b. The reason why I'm going to do 10b is because a 4th degree polynomial is a good question on either a quiz or an exam. Okay, so determine the exact roots of the following polynomial equations. And remember that, yes, we're going to confirm everything on our calculator, but you have to show your work. So I'm going to input this onto my calculator. Actually, let me start by doing the potential zeros, because they always ask that. So the potential zeros are going to be factors of the constant term. What are the factors of 15? 1 and 15. 3 goes into 15 5 times. There's actually only those 4 numbers there, but then I could make up the negative of each of those numbers, so positive or negative of each. So there's actually 8 potential zeros of this polynomial, or of this equation here. All right, let's input this into our calculator in Y1. And let's actually look at what the zeros are. So go to y is equal to, and it was x to the 4, and then this was minus 12, which I'm going to insert that, minus 12x to the 3 plus 4x it wasn't squared. Sorry. I'm going to need a 0 as a placeholder. It would have just been more efficient if I would have just cleared this whole thing. Okay, x to the 4 minus 12x to the 3. Oh, this guy's squared. X to the 4 minus 12x squared plus 4x. And then plus 15. Fourth degree polynomial could have up to 4 x-intercepts. I'm going to look at my graph. It does have 4 x-intercepts. I'm going to look at my zeros. And, oh yeah, now I remember why I wanted to do this question. I can only actually see 2 of the zeros here. So what that means, because I could only see 2 zeros here, like you could keep going up and you won't see any other zeros. What that means is the other 2 zeros or the other 2 x-intercepts, they're going to be decimals. Okay, so they're not going to be integral numbers. So right now I only know 2 of the zeros, which is -1 and 3. Those are 2 zeros. So the zeros are -1 and 3. Okay, so now I'm going to prove using the factor theorem that those are in fact zeros, right? So I'm going to use -1. I'm going to use the factor theorem to prove that. Take out that x and put in a -1, minus 12, -1 squared, plus 4, -1, plus 15. That would be 1. This would be -12 minus 4 plus 15. And this number here would give you 0. 1 plus 12, or sorry, 1 minus 12 minus 4 plus 15 would give you a remainder of 0. So p of -1 is equal to 0. Okay. So since p of -1 is equal to 0, what that means is that x plus 1 is a factor. Okay, so we would take our the root of the divisor, which is a -1, and we need to do synthetic division. I need some zeros as placeholders though, so it would be x to the 4 plus 0x to the 3 minus 12x squared plus 4x plus 15. So taking the coefficients would be a 1, 0, -12. 1, 0, -12, 4, and 15. So 1 times -1 is -1, add and you get -1. Here you get a 1, add and you would get -11. Multiply, you get 11, add, you get 15. Multiply and you get -15, add and you get 0. This is my quotient. This was a 4th degree polynomial, so my quotient is a 3rd degree. That's an x to the 3. So 1x to the 3 minus 1x squared minus 11x plus 15. Where I am at now in my factoring is as follows. My polynomial, I've just proved that x plus 1 is a factor, and that was my quotient. What I now need to do is I now need to factor this. So I need to further factor that quotient. So it's in descending degree, and I'm going to put my coefficients. I'm going to put a 1, a -1, a -11, and a 15. I'm not going to put -1 here because I've already shown that that's a factor, right? So I've got to pick one of my different zeros. If I go up here, that only leaves 3. So I've got it, the root of my divisor is going to be 3. I'm going to put the 3 there. Add, and you get 2, multiply, you get 6. Add, you get -5, multiply, and you get -15, add, and you get 0. So because the remainder is 0, this is a factor, okay? Or sorry, this is the root of one of my factors, and the factor would be x minus 3. So from here, p of x is equal to, I'm going to bring that factor down because I've already got that factor. Now I could do the factor that gives me a root of 3, so that would be x minus 3. Now I would write this, okay? That would be, this is my quotient. Remember that this was a third degree, so this quotient is going to be a second degree. X squared plus 2x minus 5. From here, this is what you would normally do. You would normally say, okay, now I could factor this because it's a quadratic. What are the two numbers that multiply to -5 and add to 2? There are no two numbers that you will find that will multiply to -5 and add to 2. What that means is this cannot be factored. Okay, so that cannot be factored. So this answer is my polynomial in completely factored form. That's the polynomial in completely factored form. Now, the question though, that wasn't actually the question, so I shouldn't have boxed it in. What it says is determine the exact roots of the equation. So I know that one of my roots is -1. That guy's -1. One of my roots is 3. What would be the roots that I would get from this quadratic? So if I look at my calculator, and I go to my graph, there was the 1. What was it? -1 and 3. There's the -1, and here's a 3. This guy and this guy are decimals. If they wanted the answer, let's say to the nearest 10th, I could do second function, calculate a 0. And I just need to find out. So I'm just going to quickly show you this one. So this one, if I go left of the 0, and then if I go right of the 0, there's that 3, right? When I check this one, it's not going to give me a whole number. Enter, enter, enter. So this 0 is 1.449. I'm just going to write that down. And the last 0, which is a decimal as well, is this one over here. So I got to get over there. Okay, I've got to go left of the 0, then I've got to go right of the 0. Okay, so that answer is -3.449. Okay, so it seems like a lot of work, which we've done a lot of work, but there's actually one further thing I need to do. The reason why I need to do, I'm going to show you this last thing, it's something from 20-1, is they use the word exact. Exact means no decimals. I've given my answers as decimals. How do I get these numbers as exact values? If you were given this in 20-1 and you can't factor it, you had to use the quadratic formula. The quadratic formula was x is equal to negative b plus or minus the square root of b squared minus 4ac all over 2a. X is equal to negative b, my b value is 2, plus or minus the square root of b squared, so b is 2, square it, minus 4, a is 1, and c is negative 5, all over 2a. A is 1. What does this give me? X is equal to negative 2 plus or minus. I want to figure out what this radicand is. It's 4, and then negative 4 minus 5 is plus 20. That's 24 over 2. You'd think that that would be enough work to get your answer. This, though, can be simplified. So the square root of 24 is 2 and 12, 2 and 6, 2 and 3. The square root of 24 can be simplified to be 2 root 6. Negative 2 plus or minus 24 is equivalent to 2 root 6 all over 2. Then I could say, okay, this, and this are all divisible by 2. So what I get is x is equal to negative 1 plus or minus root 6. That is the exact values of those two decimals, and I'll show you on my calculator. So these two decimals here, those written as exact values would be, one of them would be negative 1 plus root 6, and the other would be negative 1 minus root 6. And just to sort of show you, and then we'll be done that question. So it's like a really long, labor-intensive question. Okay, so negative 1 plus root 6. There's that 1.449, and then negative 1 minus root 6. There's that negative 3.449. And so those are the roots of the equation. Okay, so a lot of stuff is going on here. You have to remember the quadratic formula in order to get this. And your answers would be those two and negative 1 and negative 3. Those are the roots or the zeros of that polynomial function.